Recording in progress.
I will begin with some conceptual picture of what is happening. Now, I think this picture is useful to keep in mind from no, when you have any deal with model categories. I should also I mean I very apologize for my very bad English, and maybe you should ask me often what I mean in some moment. So roughly speaking, the concept of model category.
It's OUGH, a combination of letters which can be pronounced in at least five, don't remember, 7 different ways. So in this case, it's roughly.
Of course, roughly. Yeah, roughly speaking, the concept of model category aims to behave exactly like the concept of category, but like category, but allows home set between objects be topological space up to weak equivalence. This exactly derived form in a model theory. So we can consider model category as some generalization concept of category. Category have only category have only discrete sets as form sets, not arbitrary topological space up to weak equivalence. And all.
So what Arshak is saying is, I don't know why this is true, but what Arshak is saying is that every model category is enhanced in whole of topological spaces. Arshak, is this correct? Is this understanding correct?
Yes, and I want to say what this is key point of concept of model category. What this is a good way talk about
key.
Key. Exactly.
Another anomaly.
Yeah. This is good way talk about generation of concept of category with this difference what we already said. So no, and I think in previous talks we already what was said what we have literally what if C is usual category, we can consider as weak equivalence, isomorphism as weak equivalence, and all morphism as fibration and cofibration. This is a way to embed usual category in model category. And no, but in model category, fibration and cofibration, this is just tool for do some computation. I think it's right pronounced. I mean for this is just somewhat what help work with it, but not but there is but key idea of this concept in category with class of morphism, what we have in think as invertible, and I talk about this here. Here some examples, typical, usual category, old one category, and this is just a natural part of more big world, infinity one category. No, and this really, no, this literally can be defined as a relative category, category with class of morphisms, and the model structure is additional structure on this object for help work with it. Yeah.
And just a couple of remarks. So a simplicial model category is by definition enhancing topological spaces. But where do you state the same for arbitrary model categories?
Yes, I say about arbitrary model categories, and we have some. We can consider several construction from model categories to topological enriched categories or simplicial enriched categories.
Значит, Аршак, я просто немножко не понял, значит, как возникает топологическое значение в произвольной модельной категории?
Ну, в самой категории его нет.
Да, по-моему, не так.
No, it's right, but
можно придумать симплициальную категорию с такой же коммутопической категорией, правильно?
Yes, and moreover, with the same infinity one categories here. I mean, what goal of model categories typically encode some infinity one categories and infinity one category and point of no, and my point is you should think about model categories always such way, because more because model categories is a pretty technical concept, and you can often lose understand what happened, what in general if you don't understand what this is just this is just category theory for some more general concept of category. And you just and model category is just some awkward way in code with more general category with usual category.
So there's a slogan. Model categories are presentations of infinity one category.
Yes, yes.
And well, let's look at groups. Groups have presentations. But do presentations make group theory easier? Well, yes and no. It's one way to look at groups, but not the only one. And actually, for groups, there's a better way. If we make a group act on something, we are usually able to understand more about this group than just by looking at the presentation. But presentations are sometimes useful.
I'm sorry, I almost understand your question, but
это не вопрос, это такая философская ремарка, значит, что там представления групп, они иногда ко-представления, они, то есть представления через образующиеся отношения.
да.
Они иногда полезны, но чаще всего значит, чаще всего значит, такого какого-то глубокого понимания не дают. Значит, чтобы достичь этого глубокого понимания, нужно заставить группу действовать на чем-то. Ну, например, на векторном пространстве, там, на множестве, на чем угодно. Значит, which brings us to the question whether this analogy works for category theory.
I don't sure what this analogy work because no, it I mean
to some extent it does. If we have a simplicial category, what does this mean? This means we can consider maps from simplicial sets into objects of the category, which and the result will be some other objects of the same category, which is an action of sorts. Anyway, I'm sorry for this distraction. Let's just continue.
Yeah, thank you. But I can answer on question about analogy at least. I mean what analogy between presentation and object is totally true, and in group theory and in model category and infinity category, this is right. But I don't sure about analogy between rows with presentation in group theory and infinity one category, because model category is really good presentation and really good tool when you want work with some concretely infinity one category. If you have one infinity one category what you want to study, and you find some model category for it, this is very good for you. You can use it. Maybe in group theory this is not such work. No. Anyway, so on this picture we have infinity one category of types. This is this is homotopy theory. People study this infinity one category already 100 years, like top with equivalence or simplicial set with equivalence, and I also imagine here one category localization. No, if you put one category is a reflective subcategory of infinity one category, and localization is applied to home space between two objects. You can apply pin or functor, and you get more bad category homotopy types.
Well, it's not that bad.
I mean, we have all, for example, we have all limits and co-limits in category types, but not limits and co-limits.
Well, it's an interesting category.
Hmm?
It's an interesting category, which doesn't make it bad.
In which category, sorry?
Значит, категория геометрических типов, она интересная. Она, значит, это не значит, что она плохая, но, значит, она интересная.
No, I don't think so, because in real...
by the way, let me just mention a completely unrelated result. The category of homotopy types is not concrete. Which means
I know.
It does not have a faithful functor into sets.
Yes.
For example, the category of groups is concrete. It has the forgetful functor into sets, which is faithful. The category of homotopy types is not concrete, which is an old theorem of Peter Frey.
Yeah. No, I want to say what we should understand here what people really do all 20th century. People study category of types. People study homotopy limits, homotopy co-limits. This is construction here. This is just limits and co-limits here, and so on. But we cannot say about this because we don't have enough general concept of category, and only this by this reason we have so many mention about this category, but never mind. I should already move on. No, we can discuss about this later. I have many interesting concrete examples and facts. What I want to say, explain a difference between category types and type and homotopy types, and explain why people really want to study and already many years in infinity one category types. I just also explain how you should think about what you have two different categories: simplicial set, for example, and localization in weak equivalence, infinity one category type. And if what I denote it with this symbol, and usual home in infinity one category type is exactly map space, derived map space. I mean, of course, in model sense, there are map space between simplicial sets in equivalent model structure, and this can calculate how internal home between covariant and fibrant replacement, but all object or cofibrant and filling model structure, so we just need do only fibrant replacement of codomain. Okay, and also with limits, for example, limits have exactly usual universal property how in usual category theory. This property in category in infinity one category types, but when you reformulate it in model terms, you have this the equivalence between derived form in model category. Okay, and when you how you Alexei asked me now about an enrichment of arbitrarily model category. You can do it, but your definition can be some difficult, and for no, I mean people work with it, but it do text more long and less clear. So and also also we in practice almost all model category that we work with have a natural enrichment in model category of simplicial set with equivalent model structure. This allows give more simple definition for map, for derived map draft form. How I explain how I write it here. Just simply show form after cofibrant and fibrant replacement. Okay, so I should maybe remind what is the model category enrichment. I'm no in just this case. Okay, let C be complete. Simply show set an enrichment category, and on underlying category of C, we have a model
Shouldn't
structure.
there be ops somewhere? For example, the home should have a C op as one of the arguments.
I'm sorry, I don't hear.
I think there are a couple of ops which are missing. Значит, отсутствует, в общем, некоторые C нужно заменить на CO. Вот, например,
Of course, thank you. Definitely. Thank you. Yes, thank you. Yeah. First of all, what means simplicial set enriched category? This means this category enrich as simplicial. Sorry. I think we all know what is simple set enriched category. I mean, what means be complete. This category should be complete as enriched category, and this means what usual underlying category be complete, and also we have
Also,
two functors, tensoring and powering with simplicial set, which works like taking x times coproduct of object A and x times product no, object B, how I write here. Well, I mean in usual category, if you have some object A and if C is B complete, you can and let X be set and A object category C, you can consider object A power X. How A times A times A, I mean product A with A X times, taking X times for any set. But when you have simplicial set category, we have simplicial set category, we can do this operation for any simplicial set. For example, for simplicial segment, and no, this will be from just no. I think you understand my point. So and also with coproduct. Yeah, and the complete simplicial set enriched category with model structure on underlying usual category, call it enriched model category over model category if any from the following equation condition is satisfied. Okay, this condition is just simple axiom about this very famous as left Quillen bifunctor. How you should think about it? This functor is co-continuous in H variable. It preserves coproducts in H variable. So coproducts is left concept. It connects with cofibrations. So you should consider cofibration here and cofibration here. And what I write it here. You consider two cofibration and consider square which you get from this expression and this bifunctor. You consider push out, also left concept, in this square, and finally you get natural map from push out to corner of square. And this map is covered push out product F and G. And you demand what if F and G configuration when push out product is configuration, and if one of them is weak equivalence, so push out product is weak equivalence. And totally
Егор,
so-
does this make any sense?
Yes, it makes sense.
If it doesn't make sense, you should ask Asha.
Um,
Я просто сказал Егору, что нужно следить за происходящим.
Yes.
yeah, okay. And in both this situation, you have totally similar axioms, but now these functors already preserve limits in each variable, but covariant in first argument. So you consider here configurations. Here configurations. I will write it. Configurations here fibration, because here preserve limits, and also here configurations, and you consider again square, but now you take pullback, and you demand totally similar condition about when you have configuration here and fibration here. Result map is fibration and weak equivalence if one of them was weak equivalence. Okay, and important features simplicial set enriched model category following. Derived map is just simplicial map when domain and codomain is right. It's expression. And we should write it here, but I didn't did do it. From this condition, you can derive what whom if x is for example, x is fibrant object and f is configuration, when this map simplicial set in concluding model structure is fibration. No, and similar in all over cases. Okay.
Егор, значит, понятно ли вот то, что сейчас происходит? То есть, если нет, спрашивайте докладчика.
Понятно, пока все.
Okay. What is left also to authorization of model category? Let C be model category as is some subclass of morphism in C. Object that in C is S local if it orthogonal in infinity one sense, in homotopy map sense, yeah. Orthogonal for all morphism from S. I'm imagine it here. You consider terminal map from your object.
The first condition, Z inside ob C is S local if maps to Z transforms weak equivalences into weak equivalences. But we need to remember that map into Z are essentially simplicial sets, or if you prefer topological spaces. So weak equivalences means just
Yes.
weak equivalences of the geometric realizations of blah blah blah. Okay, so
Yeah.
we know what S local means now. Now, what is an S equivalence? It's
Yeah, and as equivalence is again we consider all maps which orthogonal to all S local objects. We take orthogonal 2 times with as usual pattern in one category theorem, and we have completion of class maps. We have S, take right orthogonal, and we get local objects, and again we take left orthogonal and have saturated class of maps.
okay. So for the left Bausfield localizations, we want to preserve cofibrations. We expand the weak equivalences, and so we get fewer fibrations.
Yes.
And there's the dual notion of the right Bausfield localization, and for some reason it's not as useful as the left Bausfield localization. I don't know the philosophical reason. Just at my level of understanding, it's just a fact of life.
Sorry, philosophical reason for what?
For the right Bausfield localization being less useful than the left Bausfield localization.
Because okay. I answer on it later. I think we have a very clear reason. No, at least I suppose answer, and you can consider it. So okay, and left box localization is how already read it. I think is model category with same cofibrations, and weak equivalence is S equivalence, and fibrations defined uniquely from this condition. Okay, and very important remark, what we always can assume what S is initially operations. Because we can decompose, for any maps we can decompose it as cofibrations and trivial fibrations, and take in our S with cofibrations instead initially map, and answer doesn't change because they have difference in equivalence, and we have rules 2 from 3, so no, 2 out of 3, I mean. So yeah. Okay. No, also, of course, by definition, identity functors gives is equivalent adjoint between initially model category and bulk localization, because no, but how I write it here, this functor is left equivalent functor.
Yes, so
Resource.
the one on top is the left adjoint, and the one at the bottom is the right adjoint.
Yes,
Значит,
yes, with left, with right. Yeah.
Значит, из старой C в новую C это левый сопряженный. Потому что
Yes.
значит, левая локализация. Ну, а в обратную сторону правая сопряженная.
Yeah. And because with preserved configurations, for instance, the same with preserved configurations, and not preserved fibrations, because fibrations becomes less, and fibrations already don't preserve ID cannot do it, so this is left. And interesting. Not what this clean adjoint induces on homotopic category, not just adjoint, but reflective. We left bulk localization give reflective subcategory in homotopic category C, and moreover, actually, the same picture true for infinity one category, with just only shadow of this fact, because I mean, no, theoretically we can have such adjoint in homotopic category, but not have infinity one category. But from infinity one category to homotopic category, this is always implies. And this is answer. I can say it. I can't say it right now, but in real life bulk localization, this is formalism for reflective localization in infinity one world. So reflective subcategory is the more popular and when co-reflective, because
what is reflective localization?
This just reflective subcategory. Full subcategory, and in quadrant functor have left adjoint. This is typical situation in the for algebra.
For homotopic categories, the junction we get is such that the right adjoint is a full embedding.
Right functor here is full embedding here. Yeah, homotopic category of bulk localization,
which means it has well, basically okay.
Yes. and the reflective spaghetti is very popular pattern in algebra, and no, and more concept. Co-reflective subcategory more rarely. No, this is typical for usual category theory, and no, because algebra is not symmetric concept. Algebra connect with limits, with products, and asymmetry arise from here, from algebra. Okay, no, this is very simple fact. We just need to prove what co-unit with adjunction is isomorphism. This is exactly means what your adjoint is reflective adjoint, and how we do it. We take some object x from Bauhaus localization. We want to apply right adjoint field functor, so we need do Fibonacci replacement. When we apply, but our functor is just ID, object doesn't change. When we again do cofibranch replacement and again apply ID functor, this is our result. And since these maps with equivalence in C
Since.
and since, yes, since, of course, science. Yeah. Is already the equivalence just in C, so is the equivalence is both localization. No, we have such pattern. And here we have no, these maps becomes isomorphism in both these maps becomes isomorphism in homotopy category. So our morphism from this object to this object to it to initial object is isomorphism. No, here I mean usual recept for calculate derived unit per unit from Covey book, for example, Covey book about model category. You can check it. So next next basic property with this new model structure. By the way, you should note here what left box localization can be doesn't exist. Can, yeah, and now we just assume what this exists. So when we have next property, one and two property, this is very simple. How in usual category theory, when you take orthogonal classes, you have good interference with limit and co-limit. Here you have instead usual home derived form, instead limits, co-limits and co-limits, but formal property is the same. But last property is really interesting.
Окей, Егор, значит, вот это в точности ваш вопрос, который вы задавали по e-mail, поэтому я предлагаю как следует вникнуть в этот аргумент.
Третий вы имеете в виду?
Да. Ну, значит, у нас с Егором возник такой вопрос, начну в связи с каким-то конкретным примером. Вот, значит, давайте вот сейчас значит, попробуем вот это как следует понять.
Давайте. Okay. Yeah, and this property very useful often. Okay. Now I want to say some about examples, but it it have many words, so I skip it. And first of all, we should note what if we add to our class maps which we want invertible new maps new maps which see local configuration. We have the same local objects with old and new class maps because by definition C local. No, we already assume what it is important here. What we have this model category, and as local configuration, this is left. We left orthogonal class, and right orthogonal class is all figuration in our model category. And so just by definition, any no, do you understand it? What
Егor,
I mean?
does this make any sense?
Not yet.
But why this misunderstand?
Okay. No, I didn't understand the explanation.
Okay. Again, what I mean. Now, as by the way, we assume here how I want here, what as is configuration in initial model structure. So now as here is some as a configuration in Bauschut localization model structure. because it's S local by trivial and the configuration. And what I want, what to say, what if we add any part of this class to S, and U also. Since your what is your local object? Local object is object which we write. So local object is this is object which orthogonal in map in drive map sense all maps from S. But if you have this model category, this also derived orthogonal all maps from a cyclic configuration. And if you add some new maps, local objects class of local objects doesn't change. So we have this equality. So we have this equality between S and S prime equivalence.
Понятно, спасибо.
Okay. Okay, now we need to prove next lemma. We want we want to show what some class of maps which we construct from S is S local configurations, and we can add is this to S. Okay, consider but consider F from S and F tilde, which defined such way, like as push out. We have let we have this square.
Let us have.
Thank you. Let us we have this square. Here our map F tilde, which we want to prove what is configuration first, and here so arbitrarily acyclic fibration, and we want to have lift. Have lift, won't have lift. Okay, not what here. This map. I want to say what we have this square. No, this square we definitely have, because this just home apply to maps which we have. But what about this map and this square? But this map arrives from this map. Why? uh, this map have two components, from this object and this object to this object. No, for example, let's look on this object. We have maps from B tensor no, boundary of and simplex to B tensor and simplex. Oh, I'm sorry. I say not wrong things because we now we talk not about f tilde f tilde here. We talk about map from this object to x, and when we look on this object maps from this object to x, we can by definition coproduct be taken with times how I write it here coproduct x sorry here coproduct a taking x times and it just x here, and when you can put x here, and this exactly what happened here. We can we move this object. No, okay, I think already always clear. My English is very slowly, but I think I already say what you need. So this object, and now here we just free it from home, and totally similar. We have this map from also from two part here, and this give us lift in big rectangle, and if we look now on this square, I mean with 4 objects in square, what we can see. This map is configuration in simplicial set, and this map this fibration, this trivial fibration, because it was trivial fibration, and we have simplicial enriched model category. So we have this lift here. We work just in category of simplicial set with Killing model structure. And finally, this lift literally mean map what we want, because we gain again just put this object on in first argument how tensor product how coproduct such times of B.
Егор, does this make sense?
Yes, makes total sense.
Okay. Okay. So now we only prove what F tilde is configuration. Now we need to prove what is C local. How what this mean? It means what for any fibrant as local object, we want what apply home to F tilde. We want to have what this map how big variance, yeah. We have to want orthogonal derived from in derived form sense. And so let's apply home functor to push out diagram which define this object. It here. No, I mean here is push out and here is initial square from this push out drive. And
does any of this make any sense?
Yeah.
Okay. If it doesn't, you need to ask Ashok.
Okay.
Sorry, I should to explain something again.
Нет, я сказал Джипингу, что если ему что-то непонятно, он должен спрашивать докладчика.
Хорошо, да. Это правильно. Okay. What we can see here. First of all, maps from green bullet is weak equivalence and even weak fibrations. Since our map is as local configurations trivial by trivial reason. And also this map is fibration because one second. Yeah, fibration because this just apply form factor to configuration, and this object is fibrant object, so by simplicial model category axioms we have here fibration. When here we use some important property of model category of simplicial set. In this model category, pullback of weak equivalence along fibration is again weak equivalence. This called right proper model category when with property is hold first, without this. And so this map is weak equivalence. How pullback? No, because of course push-out diagram becomes pullback diagram and under conjunct. And finally, by 2 out of 3 rules, we have this map. What this map is the equivalence how we want.
Okay.
Okay.
I think we've come to a time when we need a break. Arshak, is this the logical place to make a break or not?
It can be good place for break, yeah, or maybe after complete after finish proof.
Okay.
In our slide only when okay. So I think I'm finished now. Yeah. Okay. Now we prove lemma, and when we need proof statement, let S be new S be old S plus all acyclic configurations. No, and how we want in real, it just contain strange notation. I mean, instead it, but this just contain. Anya, I'm sorry. No. Because acyclic configuration in C, in initial model category, but this is only as local, but not cyclic. Okay. Now we want to prove what right ordinal class new S, and we know what it doesn't change right ordinal class initial S also. Right ordinal class of S is different as local object. How we want to prove. And two implication, to right, from left to right. I mean, if we take some object from right ordinal class, by definition, is fibrant object in model category because this at least right ordinal to all trivial configuration. It is already half of drop. Next, since this is fibrant, we can consider every map from S and consider such square, and since X is fibrant, and we know we already proved in lemma what F tilde is trivial with as local cofibrant map, we have lived here and in faucet localization model category. I mean, so if we again in page this map how we already do in Lemma, we can look this square and this leaf will be exactly mean this leaf. And this mean what when we fix some map f from S, we have for all n natural number this leaf. But this class map is exactly generate acyclic, generate trivial. I mean, it's exactly generate configuration in simplicial set. And right of now class, this map is exactly trivial fibration. So we have what this map is trivial fibration, and in we supply what x is s local. C local.
Igor, does this make any sense?
Yes. Like I think the segment was essentially made for little bit. Yeah.
Okay, and finally, if we take some fibrant S local object x, and we want to prove what is right orthogonal to all maps from S, and we fix some map S from S. We have this map how acyclic configuration by simplicial model category axioms, and so with configuration in what imply what is just selection on underwide sets, and this means what we have lived. No, in real usual lived condition in square diagram, this is just shadow of derived orthogonality condition. When we demand what these maps orthogonal in derived sense, this condition mean
Igor, if this doesn't make sense, then please ask.
It does make sense right now. It's not clear for me why subjective implies what we want right now.
Okay, so we can stop here. I think this is end of this.
Что было непонятно, Егор? Давайте.
Меня плохо слышно, может.
Sorry, я не понял просто. Мне Саша сказал does.
Бывает. Мне непонятно, почему из селективности следует то, что у нас слово есть поднятие.
Sorry. Okay. This is part of confidence definition. when n equals 0. Okay.
Окей, да, это понятно.
And maybe you.
Да.
Sorry. You mean this?
Да.
Okay. Okay. Sorry. I answer. Okay. This become. Sorry. This becomes. So we want to say what if we have any map from R to X, we have some map from B to X, which do this diagram is commutative. This means weak orthogonality.
Weak.
Weak orthogonality. Okay. This is exactly surjective condition this map. Okay. Thank you for the question. So we should have break now.
Okay. Are there any more questions? If there aren't, let's have a 20-minute break. Okay, I'll pause the recording.
Yeah. We now we are considering one categorical analogy of both localization. We have just usual category C, and now drive map is just usual home in category as local object is just right orthogonal objects in strict sense. What means lift not only exist but uniquely exist, and this very good categorical concept. I mean, while weak orthogonal classes some bad notation which useful for model categories, of course, because model categories is not strict concept, it's not algebraic category concept, but some technical concept for modeling higher object, but in modeling, yeah, but in normal category theory, right strict orthogonality condition give us what right and left in string sense orthogonal classes, which just closed under all limits on co-limits. No, I mean right under limits, left under co-limits. With what that this property don't hold for with cardinal classes, for example, and but this true when we consider not V cardinal classes in model category, but hold the right form in infinity category sense. Anyway, I want to consider some examples. For consider a category of group and map class map from one map factorization from free group on two generators to free abelian group on two generators. And what is S local object? This diagram means what if we just pick up any two elements in G, these elements must be commutative. So this means what G is abelian group and local objects is just abelian groups, and we have reflective subcategory, and moreover as equivalent with precisely pre-image isomorphism under this adjunction.
Chipping, does this make sense?
Yeah, makes sense.
Nice. And this picture is very typically we can ask how often this happen, and answer almost always when you have no, when you have when you live in normal category, some mathematical structures what have formalization as locally presentable category, and you when you consider any set of maps, what you need only small conditions, not big class maps. You have what S local objects is reflective subcategory. So we need to understand what is local presentable category, and I think that we should pay some attention to this concept, because this will be important later, and I think maybe it can be important part of this talk, because you should study to understand what how to check what your category is locally presented category, and for understand can you use general theorems from this talk or not. So what is locally presentable category? No, I don't want to read blue text. I hope you read it.
Okay, so I has small lambda small limits, and then there's something in the middle. The functors, the no, I for one don't quite understand what this means. So we start with what? With the category C, and then we take a small set, and then what happens?
Sorry.
Значит, ну, видишь, конечно, что происходит. Значит, мы хотим определить, что такое локально, значит, локально представимая категория.
Да.
Значит, дальше мы говорим, пусть и это множество, нет, и это малая категория. Значит, пусть у нее есть все лямбда маленькие пределы. Вот, и дальше какой-то значок. Значит, вот,
Ну,
что означает этот значок? Наверное, означает какой-то ортогонал.
нет, это просто разделитель между, ну, тут это ничего не означает. Просто у нас есть вот как бы контекст, слева написано, справа написано утверждение в этом контексте. А как бы, ну, можно формально написать импликацию, наверное, но как-то странно писать импликацию.
Значит, итого, мы начинаем с категории, у которой есть все лямбда маленькие пределы.
Да.
Значит, дальше делается утверждение, что значит, функторы из нее сет, которые, видимо, сохраняют значит, лямбда маленькие пределы, значит, и это локально лямбда представимая категория.
Да, и это как бы такое вот конструктивное определение, в том смысле, что любая категория полезно такое, это локально лямбда представимая, это полное описание локально лямбда представимого. Как вот их все строят.
Так, значит,
Потом еще будет определение интенциональное, второе, как, если он дана, как проверить, что она такая.
Так, сейчас, значит, значит, утверждает, что значит, мы должны взять значит, функторы, сохраняющие вот такие-то пределы из малой категории в сет, и вот получится, значит, вот в результате лямбда представимой категории только они.
Да, и все они. И я сейчас объясню, как об этом думать вообще, то есть, ну, как это, то есть, сейчас посмотрю на примеры, как раз вот пример написан тоже, что я хочу сказать. Да, so, вот definition one, say what all local lambda presented category are categories category of functors from small category which small category that has all lambda small limits to set which preserve lambda small no lambda limits, lambda small limits. And what here I when I said about idea, I said that all categories which we work in real life typically are local lambda presentable. And how we construct with category I from them. Let us consider category group, for example. I and pick up category finitely presentable. Maybe I won't write it such way. Find present the group. This is a small category, no, essentially small, and we have three groups here, and all another objects is quotient three groups by finite relation. Yeah, and you can see what I can say it such way. What every group here is just for equalizer. Two maps between three groups. So all objects here generated from three groups rank one, three group rank of rank one by colimit. First we take coproduct and then co-equalizer, and with arbitrarily finite presentant group. So if we consider now opposite category, this will be a category which have name finitary limit algebraic theory. Finitary here means what this category have finite limits, and that's all. And this part is constant. And now, interesting what category. Oops. Okay. And interesting how. Okay. Category of functors from E to Z. Preserve.
I
Just
can't
need
see.
it.
I can't see any.
Да,
Okay.
сейчас.
Understand. One second. It cannot be with some bad for okay. Oh no.
I can see myself.
Yeah.
That's not what you're after.
Yeah, sure. I think soon I cannot open my app with notice. I think I need to reboot my device. So
Please save the notes before restarting the tablet. Пожалуйста, сохраните записки, прежде чем перезагружать, чтобы ты не было.
my notice always saved in this app. Every second, every change
Okay.
saved. Okay.
Так, значит, того сейчас небольшая пауза, потому что нужно все перезагрузить.
Да.
So Arshak needs to restart his tablet. So there's going to be a small break.
Что? Как перезагрузить планшет? Я... все, наконец-то. Все получилось.
Так, что произошло? Мы определили локально представимую категорию, но значит, таким, ну, в общем, там, значит, таким способом, что непонятно, почему такие категории существуют. И вот сейчас мы пытаемся это понять. Так, значит, появился еще один шаг к гвоздям. Я делаю админ. Так, ну это опять я. Значит, неинтересно.
Работает?
Ну,
Ну,
что-то,
да,
да,
открылся
что-то появилось, да, вот это,
Ой, вроде таска.
Ой,
да,
не
но
то.
это уже не очень похоже, то есть это похоже, но немножко другое.
Да, вот. So, I already said here what we get finitary limit algebraic theory from category group. What means what this phrase means only category with finite limit. That's all. And we understand what, of course, finite presented groups closed under finite colimits, because what is finite colimits? It's a coproduct or co-equalizer. Coproduct is just union for any algebraic theory. Coproduct is just union generators and relations, and union of finite set is finite set, and co-equalizer is just attach relation for every generators. No, I think you all understand this. I don't need to write. And this closed under finite limits, and so this category have finite limits. And what is category functors from I to category to set? How I explain here, every object in this category is constructed how colimits
As as the co-limit.
as the as a co-limit of free objects of rank 1. So since functors preserve limits, we know what no, okay, consider this functor from I to Z. Let this functor from okay, some I need to change my notation. Let with some set X. So we know G from any another object from I. G from this object is what?
G of G of this object is this G от это G of.
Ой, I use Rush. Sorry. Of course, G of free objects of rank n.
Well, let's ask GP.
Yeah.
What is the result?
What is the result? Yeah. How somebody think? Someone think?
So sorry.
So suppose we have a function from I, which is finitely presented groups op to sets, and we know the value on Z, and we want to know the value on Fn, and we assume that the functor preserves limits.
Yes, and I is opposite. Yeah.
Yes,
opposite.
sorry, it's the opposite of finitely presented groups.
Okay.
How someone?
Well, firstly, Fn is the co-limit of the co-product of F1 n times. This we
Yes.
know.
Yeah.
And in opposite category, it is product n times. So since G preserve limits in particular products, it is n Cartesian power of X. And any maps from, no, for example, we have such maps from Z to P2, which pick up element X, Y, I mean, with free group on XY, for example, and for
X,
this
Y.
map in XY, yeah, it was watching XY, and opposite in opposite category we have map in our direction, and it was some map from X power 2 I mean stressed X to X, and if you just look on all this, you understand what even already this part already functor on free groups, and maps between which preserve products when it work from opposite category. This literally just group. This is literally group. I mean, this is literally set with multiply operation and we have map from Z to Z, which minus homomorphism, automorphism Z, and this give us operation invertible elements, and we have maps from Z to free group on zero generators, which give us maps from one point terminal object in set, preserve terminal object how empty limit is also finite limit also. So we have neutral element, invertible multiplication, and all axioms between this from from commutative diagram in this category. You can check it, and this how it works in general. If you have any algebraic category, if you have algebraic category, even you can consider only free objects and filter which preserve limit, preserve products from opposite category, and you reconstruct this category. So
sorry, we get all groups as functors from I to sets, which preserve limits. Is this correct?
Yes. Category. I understand what this category is. Category group.
Okay.
Sorry. I mean, I explain. I explain now what. Yeah.
Yegor, does this make sense?
It just make total sense. Very beautiful. Correct.
And but now we touch only free object, and for algebraic objects, algebraic concept it enough. It's but not in general. Here I said what we have metric space with morphism, which I mean morphism. I don't know how it in English. I mean contractible. No, not contractible. I mean with morphism.
Okay, let's consider this example. Suppose we want to describe the category of metric spaces and continuous maps.
Not continuous maps. We cannot continuum maps. We can with I mean with continuous maps. This is not locally presentable category, and this totally have right reason, because continuum maps, this is very soft. It don't preserve metrics. We consider metric, but continuous maps, this is just only. I mean, this is just about topology. So.
Okay, so metric spaces and Lipschitz maps, or
yeah,
or non-expanding maps.
Yes, and of course, when you consider this such way, you should allow infinity metrics. I mean, your matrix is function from
Okay.
Some points can be because if you want coproducts, you definitely want infinity distance, no natural distance between companions of coproducts.
Okay.
And
so what do we take as finitely presented groups from the previous example?
Okay. Yeah, here we need consider finite presented metric space. What is I understand now. I should to explain now. Yeah, explain. Okay, maybe this is a good moment for introduction, general concept of finite presented objects in category, because here we use algebraic concept. It's work here, but here we can confuse what is finite presented. We also can consider metric as set with structure, and I can understand in these terms also general approach, but also for two definition of for two definitions for definition of locally representative category, we need general definition of finite presentable objects. And what is it? Object A from category C is finite presented if home functor preserve filtered colimit. Filtered colimit preserves, of course. Thank you. Filtered colimit. This means diagram in C such that E is filtered category. What means just any category, any finite diagram in E has cocon.
Finite
diagram has cocon. This just natural generalization concept of direction. I mean direct poset.
Well, in particular, if we have a partially ordered set which is directed, it's an example of a filtered category.
Yeah, when poset, where we have for any finite elements and finite set elements, next elements which forward. This is example. This is literally, I mean, directed poset. This is literally filtered and poset. Yeah. But filtered is generation for category which not poset, which have many morphisms between objects, not only one or zero. And no idea is the same. What all objects move in one directions to infinity, approximate something in infinity. And such colimits should be preserved. This also totally makes sense. Just consider what finite presented objects in category set. This just finite set, because if you have finite set and such type of diagrams, what you have such diagrams and colimit. F limit F. If you consider some map from finite set to colimit F, every point here uh, you you consider some map and some point here with image with point. This point in column, so it arrived from some stage in your diagram, and with through all every point lives on some stage. This is finite set of stage, so there is some stage for them all, and on this stage you can how it say you can construct map on this stage, and so you see what set of maps from your objects in colimit is the same what colimit all maps from your objects to from your objects to objects in filter diagram. But here we need for only diff elements because sets doesn't have any operations, so doesn't have any relation. But in general, when this is not set but some algebraic structure, you need you need to find not only stage where all your generators together, but stage when also all relations between them together, but your relations are also finite, and so this stage is this stage exists.
Igor, does this make sense? Does any of it make
Yes,
any
yes.
sense?
But I already knew this example, so yeah, it makes sense.
Okay, and this is reason why we consider why this definition for finite presenter objects, not finite generated objects. Anyway, if we understand this, I can explain finite presented objects in category of metric space. So okay, I think what we should to understand now. We should understand now which objects finite presented here. We need some hypothesis for proof it because
To prove what?
I mean we need to understand which metric space looks like finite presented, and when we can prove it, and for
Well,
it.
I think let's just see the answer and skip the proof.
Oh, okay. Anyway, okay. I should explain. I should explain how you can guess which metric space is locally presented. For this, we need to think about metric space how set with operations. This definition is not such. This definition is not operations on set X with evolve some new strange set, and axioms is not just relations on operation, but some inequality. No, I mean some. No, okay. I think I explained this moment. So how reformulate metric space in terms of operations and relation on operations. We can say what yes, sorry, 1 second. For every R from for every R from
R.
R are yeah, from real numbers, we can consider
Не то, чтобы у нас, по-моему, есть куски из всех частей.
BR, BA.
Очень сложно. Мне кажется, надо подождать вклад и потыкать его типа это есть.
And this is just particularly different operations with from I mean particularly different operations from partially different operations from R to terminal set, to R and this defined when
И сам код приложения идет.
This is the main this operation. So this operation know only when two elements close with this distance, not more R and all with all. So we think about metric space how just select subsets BR for every R from real numbers, and this also explain why we have infinity, because of course union all these sets can be less than all set of parts. We don't have such axioms. This is not algebraic. We just have such operations, and what is now finite presented metric space? 1 second. I'm sorry for million types. It was our set, not fixed set.
Okay, so X is a metric space, and
Yes,
we define
yes.
the operation BR on it.
Yes, yes. But now we should understand what is kind of presented and how we can do it. It seems what it just finite. No, it cannot be. If no. What it cannot be just a finite metric space, because finite metric space, this is 1 minute. Oh, finite metric space. It can be. Okay, I have hypothesis what met is the category. Really, I should category of
Well,
finite metric
By the
space.
way, for all we know, there could be several choices for the category I, such that the functors from I up to sets are the same, which preserves limits are the same as blah blah blah.
Yes. And yeah.
And so Ashok says that if we take finite metric spaces, then this already suffices. I was going to suggest compact metric spaces, but it's a larger category.
Sorry, what about compact metric spaces?
Compact metric spaces is I think it would also do, but the problem is I'm not even sure it's essentially finite. It's probably not. Okay.
You mean essentially small?
Yes. So sorry. I'm talking nonsense. Yes. Essentially small. It's probably not.
Yes. I think so.
Okay. Anyway, but luckily for us, we didn't worry. Finite spaces would do.
Yeah. It looks right. This looks right because this category closed under coproducts obvious. Yes, and under colimits also
well,
obvious.
we need to. There are several ways to. Okay, co-products. Yes, then you use the infinity element of. Okay.
In colimits, and so and okay now we should all. I don't think I don't know why, but I should just if I know what my concept is just set with additional structure, I should guess what I just need take something what looks like 3 objects on one generator, and when take finite limit completion, I should just point and take all colimit from point, and it should be my category.
No, because if you take, for example, the co-products, you get just discrete. You get a discrete space with all distances infinite.
Yes.
How do you get something which is not infinite? Something which has non-infinite distances.
Yeah, this is good question for my last code from colimits. Yeah, you're right. Colimits cannot. But
groups are special. Groups are.
Yeah, because with algebraic theory. Yeah.
Groups of algebras over a monad in sets.
Yeah, but we can consider some
forgetful one. But metric spaces, I'm not sure. I don't think they are.
But if we consider some metric space from I mean some just finite metric space, any nevertheless and consider filter diagram and colimit. I want to prove what this is compact object, finite presentable object, and I consider any maps here, and I know what every point arrives from some stage, and I have stage some no, I have some stage here when all points leaves, always points leaves here, and I know what my morphisms not cannot only can only can on distance only small. So okay, I think I need to think about it and explain it later. Maybe it's already too far from.
Okay, so
general topic.
the conjectural answer is that we get metric spaces and non-decreasing maps as a category by taking finite metric spaces as our category I, which we start
Yeah.
with.
Yeah, but itself statement about locally finite presentable category of metric spaces is definitely true. And here I use another definition locally presentable category. I just give presentation with concept with operations with particularly defined domain and with I can give keywords with called essential algebraic theory. With like algebraic theory, how universal algebra, how group rings and so on, but here you can consider particular defined operations in controlled way. And very good and simple example, not metric space maybe, but category. Category with this.
Before we move away from metric spaces, I think the category of compact metric spaces is actually essentially small. Why? Well, because every metric space is the Gromov-Hausdorff limit of finite. Every compact metric space is the Gromov-Hausdorff limit of finite metric spaces.
Sorry, what?
Every compact metric space is the Gromov-Hausdorff limit of a sequence of compact metric spaces.
Yes.
Let's.
I understand. But also, I think we can another argument also every compact and maybe second countable topological space with subspace of some universal compact space, Hilbert cube.
Yes, yes. There's the universal metric space, which has the word Eurozone somewhere, but I've forgotten the exact definition. The idea is, as you say, it contains more or less everything.
Yeah.
Just compact topological spaces are not an essentially small category, but compact metric spaces are.
Yeah, thank you. Understand. What about category itself? This just very natural presentations with three total operation. We have two carriers with two sets for our concept, three total operations, and one particularly defined operations, but partially defined. Thank you. But domain with operations is controlled with equality, no, from totally defined operations,
Quality.
quality. I'm sorry. What? And this looks this is typical how looks any essential algebraic theory, and models of essential algebraic theory in category sets. This is all locally presentable category. This is three definitions locally presentable category, and now we can understand what is finite presentable category. This just one second. Yeah, this just interesting. What I understand how this how we can guess this answer, but I say what I will say now. What this this category, which we can construct from finite Q. How you can take free category from finite Q. You have just such type objects without composition. You have only points and arrows, and no, you can consider I arrows if you want, and you have something like that without composition. When you I don't know how example more good. No, that it will be something like that. And no, okay, ID maps. I have ID maps. And when I take free, it is finite pure. And when I take free category on this, so for every path in this category, I can use morphism, but it not so big deal because only two new morphism. Maybe, yeah. No, you can imagine in more complex examples. It can be you have category of path in your QA, and your ID maps is just empty path.
Okay, so we take basically a finite category, meaning there are finitely many arrows and finitely many objects, and all those can be represented by taking a free quiver, and then
No. This is not a finite category because this is finite. What finite presentable? То есть this means we take free category from finite Q. So if we consider, for example, Q with non-ID maps,
we have finitely many maps in a finite quiver, but when we take compositions, we get potentially infinite.
Yes. What for example, free Q for this free category from this Q. This is just monoid of neutral quiver. This is just monoid of natural numbers because free F, no, it's clear. And when we can add for compositions any finite relations in this free category. This is answer. And what is this is interesting. What category is just functor from opposite this category to set which preserve finite limits, and now with groups we can see it in details. Here in this category we have this category, this category, and it's enough for us, I think, because this category, this is some set, and this is some set, because this category construct here how push out in category of finite presentable category. So our functor preserves finite limits, and this set will be pullback, similar pullback. So maps which here was such called D1 from simplicial notation give us composition, and this enough for encode category structure. All these objects already uniquely defined this part. How in group it was from this free object. It was for group. Okay, so I hope now what you believe me, what locally presentable category is a very simple and beautiful concept. And I want to say about definition of two, if we don't have any question about before. Okay, so if you already have some category and you want to check this is locally presentable or not, you just need to check what your category is complete, and what if you pick up a subcategory of lambda compact objects. Lambda compacts, this means preserve lambda filtered colimits. This is direct generalization filtered colimits, where instead finite we say about set which strictly less lambda, where lambda is some cardinal. To be honest, limit right now, but this is too technically for. I mean, this is very simple, but we don't need to discuss this now. We just check about this. This is not. This just means what if you take a collection of sets which every sets in this collection have small elements when lambda, and all your collections have small elements when lambda. Coproduct will be small when lambda.
Okay.
You cannot.
Let's assume we know what lambda compact object is. Yegor,
Well, I understood the definition of lambda commutator objects.
Okay.
Okay,
So,
okay.
so Ashok, I think then it's probably best to write it down somewhere.
Super. So I should to say what to condition for it is every object in your category is colimit canonical diagram lambda
Ashok, if you're writing anything, then I cannot say it.
Okay. Yeah. For example, consider category group and any group G, and for example, we already understand what finitely presentable group how we discussed before it exactly finitely presentable in categorical sense, home functor preserve filter limits, and we know what we already know what is our I category, and we want to check this condition, what every group, this is canonical colimit, finite presentable groups which maps into G. What does mean? We consider next diagram. We consider all maps from all finitely presentable groups to our groups, our group G. And this category, this slice category, no, more precisely, comma category, where its objects is maps from objects E to G, and morphisms is triangle. And we consider functor from, if we want to say it very formally, we consider functor from this comma category to category group. This functor call it DOM. It just gives this object map, DOM of map. And we say what colimit with functor. No, I think more natural, some less formally notation is itself G. G can be constructed from all finitely presentable objects which maps into G. And how it works, this almost how to say what group is colimit or finitely generated subgroups, but now you don't have finitely generated, you have only finitely presentable, but you also don't need what it will be subgroup. You need only, you can consider only maps, not monomorphism. So you just I don't know what I should explain now. I think it I think what it if you understand how calculate colimit in category group, it's clear what what is colimit. Colimit colimit in category in it will be element from one from this colimit DOM functor element here is some element from diagram, and two elements is equal if they element equal if they becomes equal on some stage. So for every elements in G, you can consider just maps from Z, which pick up this element. So you already have for every element in G, you have element in the limit, and now you need to show what any other element equal this element from Z to G. No, I think it's already clear now. Yeah.
Well, sort of. Let's see. Why are we talking about groups again?
You asked me write something about the two condition, how if I correct understand you, and
okay, so the second definition of locally presented or presentable category. Let's look at the definition again. For C, C is the co-element of I, where I is lambda compact.
Yes.
Okay. Okay. So
objects construct from
Yegor and Jipik. Let's look at definition 2. Does the definition make any sense?
Yeah.
Okay.
Fine.
So Arshak is claiming that this is equivalent to definition 1, and here is an explanation why the category of groups is actually locally presented according to definition 2. We already saw that it satisfies definition 1. Well, it satisfies that definition 2 as well. It's well, it's not a proof, but it's an illustration.
Yeah. Thank you. Not you. So we have.
I don't think so. Well, we have already covered a lot of stuff today. I don't think there will be time to explain everything in the detail it deserves. So one option would be to state the theorem, and this will be it. And well, another option, if you're willing, we could have the same sort of talk next Saturday. If Yegor and or Jipping would like to know the details. Значит, того, у нас еще материала много, времени уже не так много, 4 минуты. Значит, можно сделать одно из двух. Можно сформулировать теорему и, значит, на этом закончить, и значит, а еще, значит, можно сделать еще один субботник примерно в таком же стиле, как сегодня. Если у вас есть, значит, силы и желание.
Ну, во-первых, я хотел бы сказать, что я не уверен, что доказательства... Если мы говорим про доказательства теоремы
Что мы хотим?
локализации
Значит, если есть локально представимая категория, и, значит, ля-ля-ля, то тогда локализация Боусфилда существует.
Да. И эта теорема, она довольно техничная.
Мы не хотим доказывать эту теорему целиком, но мы хотим разобраться, почему значит, с помощью какого-то дополнительного трюка имени значит, Боусфилда Смита значит, ее можно применить к топологии.
Да. Да, ну, я, в принципе, не могу подготовить еще...
Это, по-моему, ну, в общем, если вот обсуждать это как сейчас, то есть достаточно подробно, ну, это, ну, по крайней мере, на час. Значит,
Да нет, это, мне кажется, еще больше. На самом деле, там вот рассуждение, которое был Смит, оно тоже не очень, я бы сказал, что мне кажется, оно может вполне все 3 часа занять, если подробно обсуждать его, потому что ну, там довольно такая техничная дифференциальная техника, я столично говорю немного, но, в общем...
Так, хорошо. Значит, давайте подойдем с другого конца. Значит, Аршак, если у вас, значит, сила желания вот это вот, значит, рассказывать, значит, ну, там, если там нет и того или другого, тогда вполне можно сейчас сформулировать теорему, поставить точку. Значит, а если...
Да, я тоже к этому склоняюсь, с одной стороны. С другой стороны, тут на самом деле для формулировки теоремы тоже еще есть что оценить и что понять, потому что, ну, то есть, как бы, если все, конечно, быстро проговорить, то можно успеть, но в этом, мне кажется, немного смысла, то есть стоит, как бы, разобраться со всеми понятиями, которые возникают, как вот
Хорошо,
сейчас.
значит, если у вас, значит, желание и силы, значит, чтобы продолжить через неделю.
Ну, да, я бы мог рассказать это вот в нормальном виде как бы до конца, но я не могу точно сказать насчет следующей недели, потому что у меня сейчас все экзамены на этой неделе, и я не уверен, что в субботу ничего не будет, но если уже... ну и что я там буду как бы как-то в состоянии. Вот.
Какие экзамены?
Но я точно... Но неделю через нее, 8 числа, я точно могу. Там, ну или, в общем, когда-нибудь.
Так,
Ну,
хорошо.
может быть, и первый.
Значит, теперь, well, let's ask Yegor and Tipping. If Arshak would you be interested in learning the proof of well, at least something about the proof of the localization theorem and applications to topology.
Ну да, самое интересное.
Okay, so well, at least Yegor seems to be interested. Okay, so let's in this case let's state the theorem. Well, we basically have it on one of the slides, and then hopefully we'll cover the rest at some point, not next week, but at some other point.
У нас есть задачи, которые относятся
То бишь, значит, тогда давайте сформулируем сейчас теорему, ну, она уже, по сути, сформулирована где-то на слайде, и, значит, и на этом поставим на сегодня точку, но в надежде, что где-то через пару недель мы продолжим.
So, how I already said, if C is locally presentable category and C is locally presentable category and C is small set.
The other way around, C is locally presentable and S is a small set.
Yes, C, of course. When S local objects form a reflective subcategory, and as equivalence exactly is precisely pre-image isomorphism under reflect after reflector and with reflective subcategory is exactly localization in universal property in universal property sense. This is classical result from theory of locally representable category. I highly recommend Adam Rositsky's book. Just first capture this book already contain all ideas which I talk today about locally representable category, all this definition already first capture.
Chapter. And what does capture mean?
Что значит,
Sorry, I mean chapter, I mean
А capture это поимка.
я имею в виду первая глава.
Yes, so chapter 1 already contains this theorem. Okay, well, I don't think we really need to see all the details, but I would like to see how it applies to cohomology theory.
это то, что мы информацию
I'm sorry, there is noise.
Значит, ну, если, да, значит, я не предлагаю в следующий раз рассказывать все детали доказательства, но, значит, оно, скорее всего, длинно и муторно, бесполезно. Значит, но...
Не, вот у этой теоремы, на самом деле, которая чисто категорная, у нее вообще доказательство довольно концептуальное, это называется аргумент малого объекта, там так более-менее, и...
ну, если доказательство, ну, такое, значит, перевариваемое, то тогда почему бы и нет?
Это было бы интересно, мне кажется, с одной стороны, но с другой стороны, это как бы... Я не знаю, сколько это может занять. Это может занять, в принципе, и там более-менее почти все 3 часа, может быть.
Но,
там, потому что...
Да, давайте рассчитывать все время так, чтобы осталось, ну, чтобы это не затягивать на там какое-то бесконечное время, и чтобы осталось какое-то время на приложение.
Ну, и только сейчас еще раз уточню, что это просто теорема про категорию, тут ничего про модельный нет.
Так, хорошо. Значит, сейчас, на секунду. Хорошо. Значит, хорошо. Да, вот, а как, да, совершенно верно. Значит, как все это свести, то есть как это применять к локализации Бусфилда?
Да, это как бы то, что мы давно знали, как в теории категории, ну, не то чтобы давно, точнее, но на лет 15 пораньше, видимо, или сколько там. Короче, да, а потом вот уже в конце 90-х люди развили как бы уже теорию локально представимых модельных категорий, которые называются комбинаторные модельные, и доказали там аналогичную теорему. И вот я про это буду дальше рассказывать, но там, мне кажется...
Она есть на слайдах?
Ну, я еще не показал ее, дальше.
Сейчас, где она?
Вот.
Так, значит, left prop, combinatorial, да, хорошо. Значит, тогда существует, ну, да, то есть, ну, и вот эта теорема нас интересует там больше, чем предыдущая, которая там просто теория.
Ну, я не знаю, как сказать. Вот, потому что эта теорема про просто категории, она, это вот такой краеугольный камень математики, аргумент малого объекта. А вот теорема Смита, ну, она очень сложная, мне кажется, но...
Ну, значит, если сложно, то давайте просто поглядим на формулировку, полюбуемся. И, кстати говоря, вот такой вопрос.
Ну, я еще тут, как бы, чтобы ее обсудить, извините, что прибиваю, еще вот я хотел рассказать, что такое комбинаторная модель, наверное, я не знаю, это Миша рассказывал там или в декабре?
Нет, про это мы, значит, мы не рассказывали, но, естественно, хотелось бы Хотелось бы, значит, ну, хотя бы на уровне определения это, значит, это понять.
Ну да, вот
Значит, значит, вопрос такой, вот давайте еще раз посмотрим на вот эту теорему, которая, значит, которая на следующем слайде.
Как это понять?
Значит, left proper combinatorial, so this is the big thing. Suppose we have a left proper combinatorial. Well, we already know what this is. If
combinatorial this means locally presentable and coefficient generated. То есть with coefficient generated is to be honest, this just means what not only category generated small data from small subcategory E, what controlled small data, but and model structure. Define small data.
We already had we already saw configuration generated model categories in one of the tools. We just didn't see locally presentable categories, but we did see configuration generated categories.
So,
but basically, it's the job half done. Anyway, so suppose we have left proper C, which is left proper combinatorial and it's a model category, and then there's left pulse with localization with respect to any small set of morphisms. Now, which which of the properties are preserved? Which of the two properties are preserved when we take the localization? Left proper is it preserved?
Yes, all property,
I think it's preserved. Well, combinatorial. What does it mean? It means finitely presented and coefficiently generated.
Locally presented.
Sorry, locally presented and coefficiently generated. Well, coefficient generation is preserved.
And locally presented also. Yeah, all this property preserved, yes. And if C is simple, so it's simple also simplicial, then also, yeah, also.
Okay, so suppose we have a simplicial left proper combinatorial model category, then the left pulse field localization is also simplicial, left proper, and combinatorial. Well, it's a good thing to know. Left proper combinatorial. Okay. Well, I think I, for example, would be interested to listen to the second part of the talk. Arshak says he's willing to continue, but not next week, the week after. Well, very well. So let's see. Are there any questions? Okay, so there don't seem to be any questions, so we'll stop